you want?
Yes.
Oh,
I guess so.
Stay behind
Okay. Oh, wow. We've already advanced. Okay. Good morning, everyone. I'm glad you made it here without melting. And so we're going to kick off with a sort of grand overview of observations of terrestrial exoplanet atmospheres. And I love how the organizers snuck this in to really make sure I included Trappist-1 in my talk, which I will. So including Trappist-1, I like to start off with just an overview of what we've previously done. So not considering JWST first, but looking at what's been done with HST and ground-based observatories from the ground. This is a visualization of all of detections, not just terrestrial planets, ranging from super Earths. This graph is ordered in size of planets, so from the Earths all the way out to the Jupiters, and it's color-coded by all the different types of molecules and atoms that have been detected in various exoplanets. And it's amazing to see this awesome chemical diversity that has been detected in all these different types of exoplanets. But of course, the question here for this talk is, well, what about the terrestrials? And in designing the talk, I really had to first think about where I was going to put this cutoff for what is terrestrial and what is not. On Monday, you all learned from Heather Knutson's talk about the evaporation valley, this in frequency space, this phenomenon that happens where you get a peak in frequency that we sort of refer to as the super Earths, sort of around this 1.5 Earth radius range, followed by a dip, which we refer to as the evaporation valley, and then another peak in frequency that signifies this subneptune population. And the subneptunes we kind of think of potentially these rocky planets that might be enshrouded in these hydrogen helium envelopes, and the super Earths, more terrestrial atmospheres that aren't able to maybe accrete this hydrogen helium atmosphere. And this cutoff of the evaporation valley is sort of at 1.8 Earth radii. And so for this talk today, I'm going to focus specifically on everything less than 1.8 Earth radii, though I think that this is sort of a fairly arbitrary cutoff that I've decided, and I think it's still sort of out to see what is the transition between these super Earths and the subneptunes. So now here is a visualization of the zoom in of all of the Hubble and ground-based observations that have done of planets less than 1.8 Earth radii. And I'd like to give a plug to the IAC community database for exoplanet atmosphere observations, which I've used to make some of these visualizations. It's a really awesome resource that gives sort of an overview of everything that's been done for exoplanet atmospheres, or sort of by the papers that have been discovered. And so you can play around with it and make really fun visualizations of all of the different discoveries that have been made for different planets. And so I highly encourage you to check it out. You can see that there have been sort of a dozen and a half-ish observations of terrestrial planets. And here on this plot, that's only everything less than 1.8 Earth radii. That means that we're looking at things sort of about less than 10 Earth masses. They range in temperatures from planets around 200 Kelvin that might be, something that you would consider potentially habitable, all the way out to more highly irradiated systems that are, over 1,000 Kelvin-ish. One is all the way up there at around 1,400 Kelvin. And you can look at this also in temperature, look at them in terms of the temperature of their host stars. And you can see that all of these systems sort of orbit stars that are less than 4,500 Kelvin. And of course, that's because smaller stars, it's easier to observe the small planets because the area of the planet to star area ratio is more favorable. So you can really potentially start to see signatures around these small stars. And you can see those beads of planets down at the bottom at 2,500 Kelvin is the Trappist system, which orbits a very, very small star. And I will start out by pointing the obvious that there are only two sort of colors in this space of potential detections. And one is a tentative detection of water in LHS 1140b, and the other one is this tentative detection of HCN in GJ 1132b. So I kind of want to go through these discoveries or tentative discoveries and sort of highlight some of the history with these observations. Starting with the system LHS 1140b, which is a very cool system. It's, well, cool and cool. 200 Kelvin, so kind of puts it right in the habitable zone ish, and is a little bit on the bigger side, so about 1.6 ish Earth radii. One of the first observations taken was by Hannah Diamond Lowe in 2020. And here we're showing ground-based data taken from 600 to 1,000 nanometers, and overlaid are these 1 times 10 times solar metallicity models. And I want to give some context for why we choose to show these 1 times 10 times solar metallicity models up against the data of these terrestrial planets. So for reference, if you're not used to staring at spectra for all eternity, a 1 times solar metallicity model means that the system has something like 99.9% hydrogen helium. So that's a very thick hydrogen envelope. A typical hot Jupiter might have something like 3 times solar metallicity, and that means it's going to have about 99.7-ish% hydrogen helium. Moving down to sort of a smaller, potentially cooler, warm Neptune-ish type planet that might be more enriched in metals, you would expect that system to have something like 100 times solar metallicity, but still that means that we're looking at something like 91.1% hydrogen helium. So these are still very thick hydrogen helium envelopes. And then moving all the way down to something that would be like a temperate Earth or an Earth-like planet, now you're starting to see the regime that we're operating in here, where you have really small spectral features, and we expect them to potentially be CO2 dominated and have on the order of maybe 0-ish% hydrogen helium. So why do we show these solar metallicity models against the terrestrial planets? That might be kind of confusing, especially when, if you look at sort of the radius mass space of small planets, these are constant density curves. I think Heather showed some of these as well on Monday, you might remember. So the terrestrial planets are slated to have maybe rocky cores that are made up of maybe pure silicate, between something that's pure silicate, maybe pure iron. And if you inject just 1% or 0.1% hydrogen helium into these systems, you see that the radius kind of explodes. So we really don't expect these rocky planets to have really more than 1-ish% or even smaller hydrogen atmospheres. And this figure is taken from annual reviews by Robin Wordsworth and Laura Kreidberg on atmospheres of rocky planets, which I think is a great resource if you're interested in reading more about this. So the question is, why are we showing these 1 times solar metallicity models? And the answer is, well, at high SNR, you're able to see all these really nice spectral features. And so you can play around with doing these really nice Bayesian inference analyses like you did in the hands-on session yesterday from Paul. Also, Mike Line gave a great talk about this as well. And you can get these really nice constrained atmospheric parameters with upper and lower bounds on the parameters that you're interested in getting out. But at low SNR, you really don't have that luxury. And so you're sort of left with this rule out method where you are trying to determine what metallicity in cloud space you can rule out. And the reason why we choose metallicity is because it offers a really good proxy for feature size. So as the metallicity increases from about 1 to 10 times solar, your feature size is expected to increase a little bit because you've injected a little bit more metals into that, increasing the size of the absorption feature relative to the continuum. But then beyond that, those same heavy metals are starting to contribute to your mean molecular weight, shrinking your spectral features, and so you start to get this drop off. And then you can see, though, that those different curves are indicating different cloud pressure levels that might be in the atmosphere. And so by using just the simple way of comparing your line strength or your feature sizes to your data, you can get an idea of what scenarios you could potentially rule out. So going back to this, now you see on this plot, the significances there are indicating at what confidence these observations were able to rule out those scenarios. And in this case, the data weren't able, so a confidence of around 3 sigma is something that might be considered, you can confidently rule that out. Here at about 1.7, 1.5 sigma, for these systems, they weren't able to rule out even those specific scenarios. The following observation using Hubble of LHS 1140 saw maybe a potential water detection at a very low significance, albeit around 2.3, 2.6. And so maybe water was present in there. But interestingly enough, if you stitch the Hubble observations with the ground-based observations, it now starts to look like maybe the spectrum that you're seeing is just stellar contamination and not necessarily from the planet itself. And interestingly enough, if we move to the Trappist system, you see a very similar story where, well, the Trappist system, if you're not totally familiar with this one, it is the reason why we're so gaga over it is it's 7 planets, all about Earth size, and they're receiving installations that sort of take you between Mercury and Venus all the way out beyond Mars. And so depending on how you define your habitable zone, there could be potentially 3 or 4 of these Trappist systems that could be potentially habitable. And so it's an excellent laboratory to test sort of different planetary atmospheres hypotheses. And the Trappist system has been observed currently with Hubble and also ground-based facilities trying to look for really thick extended atmospheres. And the very first spectra, we're able to rule out, again, you're seeing these like hydrogen-rich scenarios plotted up against the data, and you're able to rule them out at sort of 5, 10 sigma. And so they really weren't synonymous with these big hydrogen-helium envelopes. But further analyses of these data showed really how stellar contamination can overwhelm the planetary features, especially in these low resolution regimes, because these M dwarfs have absorption features themselves. Those absorption features can be imprinted on the planetary spectra. And so I think this points to sort of the very first lesson learned for terrestrial planet atmospheres is, especially for these small planets where you're trying to dig down into the noise and find these spectral features, you really have to deal with stellar contamination. And also you really need broad wavelength coverage to robustly make inferences regarding these observations, especially when the feature that you're looking at is so tiny. You need additional context to really be able to say whether or not that feature that you're looking at is real. So moving on, the next system that I want to talk about is GJ 1132. This system is a little bit hotter, a little bit smaller than LHS 1140, sitting at around 500 Kelvin. It's pretty similar to a lot of other systems in that sort of orbiting around 3,500 Kelvin host stars. And 1132 is interesting because it showed this potential absorption of HCN, which is funky. The very first observation, also taken by Hannah Diamond Low in 2018, didn't show any huge spectral features, but they were able to now rule out at least 1 times solar and 10 times solar metallicity cases. And then the Hubble observation, initial analysis of the Hubble data showed this spike sort of in the regime of where you might expect HCN to absorb. Now, reanalysis of the data by 2 different groups, though, showed something, told a completely different story. You no longer see that sort of spike that was synonymous with the HCN data. And furthermore, you can see that 2 of these analyses sort of line up fairly well, and 1 maybe could be an outlier. And if you look further at the Libby Roberts analysis of the data compared to these different 1 times, 100 times, 300 times solar metallicity data, we're now able to rule out scenarios up to 300 times solar, which is great. But again, there's no big whopping spectral features that sort of jump out at you. And so suggesting that maybe GJ 1132 still has some issues to be worked out. And I think the lesson learned here for terrestrial planets is really along the lines of reproducibility. I think you all have experienced this, especially through the Eureka analyses hands-on sessions earlier this week, where all of these little nuances in the data reduction really stack up. And again, especially for these terrestrial planets, is super important to have multiple different data reduction methods to really trust what you're seeing and believe that the features that are popping out of the spectrum. And so now we're going to move to LHF 3844b, which I think is another interesting system, because so far we've really only been talking about terrestrial planet observations of these systems, or sorry, transmission spectra observations of these systems. And LHS 3844b was a phase curve. I think Laura talked about eclipses and phase curves on Tuesday, which is great. So you learned about these different types of observations. And the interesting information that you get from phase curves is you're able to create an approximate temperature map of the system. And that temperature map gives you very interesting information about how heat is recirculating in that planet. Now, if you measuring the temperature map of this system, it was clear that there was maybe no heat recirculation that was happening, suggesting that maybe that there is no thick atmosphere at all on this particular planet. I should also mention that one difference between LHS 3844b and the previous system that we were looking at is this system is quite a bit hotter. We moved from 500 Kelvin, now we're at about 800 Kelvin, and I think the specific temperature that was measured is about 1000 Kelvin. And so the other interesting piece of information that you get from this observation is this specific temperature measurement. And the interesting thing about this is surface materials themselves on these planetary spectra have different absorptive properties. And so by measuring the temperature that you're looking at compared with what you would expect from different surface emission spectra, you can actually start to make inferences about what you think the planet's surface composition is. And so looking at these spectra, the authors were able to sort of put a confidence at 3 sigma that the surface is maybe made of some combination of basalt and ultramafic rock, which is similar to what you see on Mercury. And so the lesson learned here is null results are still very informative. And also there are many different techniques that we can use to understand terrestrial exoplanet atmospheres. And we really need to be using them all to give us all of this nice context for what the atmospheres of these planets are really telling us. And of course, all hope is not lost if you're feeling helpless. I used to really think about this as future capabilities, but now we're really in the present of JWST observations, which is incredible. Compared to Hubble, JWST extends the wavelength coverage and precision by a lot. Here I'm showing sort of an approximate single transit precision, what you would get based on different stellar magnitudes ranging from 7-ish, which is about the brightest thing that JWST can look at, all the way out to about 14 microns. And I'm putting there Trappist-1 for context, because Trappist-1 really isn't a very bright star. And so the precision that we can get on that target is not as high as maybe the precision that we could get around something that's a little bit brighter. And for context, if you look at a simulation of Julian DeWitt's Hubble data compared to, for example, simulations of what we expect to get in one of the first JWST programs, you can see that the difference is huge. Compared to the Hubble data, which got precisions of around 200 ppm, we expect to get precisions of around 10 ppm for the very first observations of in this case, Trappist-1e. And so JWST, of course, is going to deliver much higher precisions than what we previously had with Hubble. Now, again, for context, hot Jupiter atmosphere spectral features, like I showed in that spectra before, have these spectral features that are in the hundreds of ppm. So you can do a single visit and be good and get great data. terrestrial planets are sort of always kind of down below the minimum precision that you can get in a single transit. And so for terrestrials, you're always going to be stacking multiple observations to try and build up the precision that you need to be able to detect anything. And so just use that for context. Even for JWST, we're going to have to wait to build up the precision to do nice detections. Now, here are those previous observations from Hubble and ground base, and I'm going to now overlay what we're doing in just cycle 1, cycle 2 of JWST. So just in a couple years, you can see we're already filling out this parameter space in a whole host of different ways, right? We are looking at terrestrial planets with transmission geometry, in emission geometry, and also utilizing phase curves. And what I think is really cool is that for some of these systems, you can see that multiple techniques are being used to tackle similar planets. And so we're going to start to build up a lot of context for these different types of planets. In total, there are about 89 visits devoted to terrestrial planet observations spread across about 26 targets. That gives you an idea for how many visits each target needs. And some of those are in multis. So in total, we're looking at about 24 systems, and it's possible I've miscounted 1 or 2 here and there. And of those, only about 4 or 5 are in the habitable zone, depending on what your definition of the habitable zone is. And I think 3 or 4-ish of those are the Trappist system. Now, what I think is interesting about looking at these selections that came out of cycle 1, cycle 2, is they all kind of center around 3 main goals. The first, which I put in its complete own category, is do the planets of the Trappist-1 system have atmospheres? Do they have biosignatures? The second, especially going to these sort of larger planets at around 1.8 Earth radii, is there a compositional divide between these super Earths and sub-Neptune atmospheres? Remember, I did this very stark cutoff right at 1.8 Earth radii, but it's possible that there is a transition between a sub-Neptune, a super Earth and a sub-Neptune, and I think people are very interested in that as well. And then the last one is sort of more generally, in addition to the Trappist-1 system, do M-dwarf planets have atmospheres, yes or no? And I think what's interesting is cycle 1, it looks like that there was a big push to do transmission observations of those planets. And in cycle 2, the strategy has switched to sort of being a little bit more skewed towards emission observations, which I think is great, right? It shows balance. It shows that we're utilizing as many techniques as possible to try and understand these systems. So of those, there have been only 5 currently published observations. So we still have a lot of data that's currently being analyzed as we speak. And one of these currently published observations was used for commissioning of MIRI data by Tom Green and Taylor Bell and collaborators. And so, but there will be additional observations of the system. And so we sort of need to stay tuned for that one. I want to highlight just 2 of these in the last 2 minutes that I have. The first one is the very first transmission observation that was taken of a terrestrial planet. It has many names, some most commonly referred to, I think, as LHS 475b. And the spectrum of this planet is, again, no big spectral features immediately jump out at you. However, you can see that now the models that we're using to compare to the data are much more synonymous with what might actually be a terrestrial planet. So you can see how much the precision gains has enabled us to rule out more scenarios for these planets. And so the models that now we're using to compare to the data are, clear CO2 atmospheres, methane atmospheres, and even an Earth-like atmosphere. And none of them can necessarily be picked out over the other, but I still think it shows progress in terms of what sorts of, what we're able to do with the data. The next observations are of Trappist-1b, 1c, and these were used in a very similar way to the LHS 1138, although they weren't full phase curves, they were measurements of the dayside temperature. If there was a big whopping CO2 detection in one of these atmospheres, that CO2 would be absorbing high up. That means the temperature that the authors would have measured would be a little bit cooler. But for 1b and for 1c, there were no detectable CO2, and this hot temperature for 1b and 1c were both consistent with potentially no atmosphere at all. However, and I will use my last 30 seconds to say, we're really only at the infancy of these observations. So the Trappist-1 system specifically made up 11% of all cycle 1 time. And I'm only showing a very small fraction of those observations. And really, actually, I think there's sort of consensus the community wants more. There have been these studies previously that have shown that in order to really robustly look at the Trappist-1 habitable zone planets, you might need something like 10 transits. And the most transits that we have for a system in Trappist-1F is about 5. And so we're really only maybe about halfway there. And so my conclusions, null results, still results. Broad wavelength coverage is really needed to robustly interpret spectra of terrestrial planets, and we must think about reproducibility when we're analyzing these data. I think we are doing this, but we need to continue using many different techniques to study these planets. And again, we're really at the infancy of these terrestrial exoplanet observations, so there's lots more to come. And then, like I said before, here's a QR code for this annual reviews of atmospheres of rocky exoplanets. I think it gives a great overview of all of these topics if you're interested in reading more.
Hi, thank you. Thank you for the great talk. Is stellar contamination something we can average out by stacking more visits, or is that too optimistic?
Yeah, that's a good question. I think it's sort of left to, I think we still need to understand more how well we're going to be able to stack visits. Part of the problem is currently, if you, let's say you propose to observe four visits of Trappist-1, there's no guarantee that those visits are going to be scheduled one right after another. And so every single visit is going to have different systematics, is going to have different stellar contamination. And so it's going to be very challenging to stack all those observations. You can use some mitigating effects. So for example, in both of the cycle 1 large programs focused on terrestrial planets, all of the observations were taken closely, and we made it so that our observations were all taken within one stellar rotation period of the star, which is great, right? However, if someone wants to follow up on that observation and add to what we've previously done, then it's going to be harder for them to combine their data with what we've previously done. Yeah.
Great talk, Natasha. Earlier, we heard that transmission really gives you sort of a lower bound on the presence of atmospheres, but it seems from your talk today, emission is much better at getting at sort of the true situation on these planets. To what extent does emission suffer from the same sort of constraint problem rather than, definitive evidence?
So it's a little bit different. I mean, they're completely different. And I think the big thing is that there are many terrestrial planets that we just can't measure eclipses, right? T to the 4th is really a pain. And so you're accessing different planets from both of those techniques at first, in the first place. It does seem like for these systems, measuring the temperatures gives you sort of still, I think in my talk, I really did sort of hint that it was no atmosphere. But there still is a limit there, right? In terms of what you're meaning by no atmosphere. So I think it's possible that I was a little loose-lipped with using that phrase. In both cases, you are really putting limits on the presence or absence of an atmosphere. And using both methods, like if you have the opportunity to use both, that's really sort of the best way to observe those systems.
We have an online question asking any chance that JWST will be able to capture a reflectance spectrum of a super Earth rocky planet?
That is very unlikely, unless it was like, I don't know, a mirror or something and it was very large. the signal of the reflected light is related to the ratio of the radius of the planet and the star, and it's very unlikely that you would be able to physically see the reflected light of a terrestrial planet. Also, JWST's precision really starts to drop at around 0.6, everything shorter than about 1 micron. And so reflected light with JWST is just going to be I would say physically impossible.
So we last had a Sagan Summer Workshop on exoplanet atmospheres a little over 10 years ago now. In that time, as you point out, a lot has happened. If you were to give this talk again in 10 years, where do you hope the field is?
10 years of JWST science. I either would be standing up here being very hopeful, or I would be very doomsday. I think it's still one thing that I didn't really have time to get into is this concept of this hypothetical cosmic shoreline. The idea that if you measure this, just the amount of irradiation that these terrestrial exoplanets are receiving, and compute what the approximate escape of the atmospheres are, these very first JWST observations that have been taken could potentially have blown away atmospheres. And so I think we're really at the infancy, and it's possible that in 10 years, we will have uncovered that many of these systems have atmospheres, and it will be very interesting looking forward to sort of the Hab Worlds, to Hab Worlds type missions. But I think regardless, in 10 years, I'm going to be super excited for reflected light.
All right, on that